Good evening, everybody. Thank you very much for coming. My name is Jerry Graham. I'm the chair of the Prototype group, and it's my great pleasure to welcome you all here tonight. A few little nuts and bolts that I have to go through, so we do not anticipate a fire drill tonight. So if the bell goes off, it means there's a fire. In which case, I've been coming here for quite a while. I've never had it happen yet. You can leave through the back doors and you can leave through the front doors. You need to collect yourself in front of the Intercontinental Hotel, which is in that direction outside the front of the building. I turned my phone on to silent, which means the only noises it will make is if it tries to communicate with anybody and I get a bit of pickup on the microphone. So I apologise in advance for that. But you're quite safe because you can't buy donuts at this time of night, so we can't force you to feed anybody in here if your phone goes off. This is the 50th Cierva Lecture. I think it says so there. Yes, it does. And even here as well. This is the 50th Cierva Lecture. The first lecture was given by a gentleman called Dr. Bennett. And Dr. Bennett worked for the Weir company as chief engineer, and he essentially succeeded Cierva as their technical lead after Cierva's death. He moved to Fairey in the latter part of the Second World War. At Fairey he was famous for the Gyrodyne, the jet Gyrodyne, and the start of the Rotodyne. He left Fairey and to work for Hiller before the Rotodyne actually flew, but his lecture 50 lectures ago was on the subject of the Autogiro, and he had seen the Autogiro grow into the helicopter, grow back into the converter plane Autogiro as a Rotodyne. I can't think of a better person to have given that very lecture in honour of Cierva, and I'm sure tonight we're going to see the full circle of 50 years of development since that time. I wonder if I could invite the President of the Society to come to the stage and just introduce our speaker.
Well, good evening everyone, and I am very privileged, I think, to invite David Groen to present this lecture. I've got his very extensive CV here. President and CEO of Groen Brothers Aviation, but also on a sideline writing novels, quite exciting novels about the Huey. He's got a very extensive experience in helicopter flying, and looking through his both military and commercial experience. Military goes without saying, but emergency medical services and quite a lot of exciting things. I came across the fact that he's also been a tour guide, but I thought, well, that's a bit boring and frustrating given all the other things he's doing. But then I thought, well, hang on, if you're a tour guide in the Grand Canyon, you know, that's pretty exciting stuff as well.
It's not supposed to be.
But if you're not piloting, if you're a passenger, it's pretty exciting, I think. Well, he and his brother founded GBA with the goal of rediscovering and developing the science of sustained autorotative flight. And as an Avro apprentice, I warmed to the idea of, with current technology, putting an Avro 504 modern composite fuselage and seeing whether we can get close to 400 miles an hour. I think that might be a bit of a challenge, but according to your design studies, something is feasible along those lines, and that really would be quite amazing if we could do that. He's also a member of the Board of Governors of the IAA, and has recently given a principal keynote address to the Chinese International General Aviation Summit. And clearly we could see great many opportunities there for gyrodynes. Well, on the 50th anniversary of the Cierva Lecture, I can't think of anyone more suited to present revolutionising vertical flight. David Groen.
speechless, which is, of course, not the thing to be saying at the beginning of a speech. But let's see if I can cure myself of that. Again, thank you so much. This is a great honor to be here today, to be invited here to speak to this group at all, let alone on the 50th anniversary of this lecture series. Juan de la Cierva's efforts in sustained autorotative flight have been a key element to rotor wing flight. What he did solved the problem of the symmetry of lift and made helicopters work today. The evolution of that form of flight went through the gyroplane into helicopters and now back, we hope, into sustained autorotative flight aircraft again. And not to replace the helicopter, but simply as a third form of flight that we think has a rightful place in history. As was mentioned, the first Cierva Lecture appropriately was given by Dr. Bennett, and who led the first Gyrodyne team. I think it appropriate, too, that this 50th anniversary lecture be specific to gyroplanes. And in this case, what the company my brother Jay and I formed 25 years ago, have been doing since, in order to try to bring to the modern age this wonderful form of flight. Rotor wing aviation was born in Spain nearly 90 years ago with Juan de la Cierva's first flight of his Autogiro. And Autogiro was a trade name belonging to the Cierva company. The FAA now calls this form of flight gyroplane. Gyrocopter is another trade name belonging to Benson, which is where it started for me. Gyroplanes are stable. They attain vertical takeoff and landing, and in some cases even aerobatic flying. This, of course, is one of the few images of the very first flight of Cierva's gyroplane in 1923. Pitcairn did vertical takeoff as a jump over a 36-foot pole, and one of my most favorite of all images is this image of Wing Commander Ken Wallace with hands and feet off the controls flying by in a gyroplane of his own design. I'm highly honored to note that Commander Wallace is here with us tonight. I'm astonished to see you here and delighted to see you here, sir. Captain John Miller, who died at 101 years old just a couple of years ago, flew hundreds of aerobatic performances, loops, rolls, Emmelmans in PCA-2, one of these gyroplanes, which he said up until his last that he thought that the PCA-2 was the safest aircraft he'd ever flown, at somewhere around 36,000 hours when he stopped counting. A marvelous fellow. Well, our Hawk 4 gyroplane is vertical takeoff and landing, is hands-off stable, but not aerobatic, at least not while I'm on board. Helicopters could do one thing gyroplanes can't do, and that was to hover. But to do so was at great cost in complexity. To give up that splendid simplicity of the Autogiro allowed it to hover, but made for aircraft that are certainly astonishing, but a whole bunch too making them work. In an attempt to get back to the splendid simplicity of gyroplanes, the helicopter world built tip-jet-powered rotors. And the tip-jet-powered rotors simply removed the cost, complexity, and failure modality of transmission-driven rotor systems. No torque to the airframe, therefore no tail rotor, none of the complexity that helicopters needed in order to hover. But there was one uncurable drawback to the tip-jet helicopters, and that was the terrible fuel efficiency. The Hiller Hornet burned its 50 gallons of fuel in 20 minutes would fly 60 miles an hour. You know, so for a helicopter that could at maximum range go 20 miles was not much use. However, they were stable. Again, you see this hands-off stability. Right? There are some Hiller pictures where you see the pilot in the cockpit doing this too as well, but that was the one most easily visible hands-off, hands and feet off the controls for the same reason that a gyroplane is stable, and that is that the rotor is turning itself rather than the airframe trying to turn the rotor. Hughes built a couple of different tip-jet-powered models, including what is still the world's largest rotor system on any helicopter, more than 150 feet in length. There are a couple of Russian designs who've picked up more weight than that aircraft did way back then. There was a way, however, to get both the many cost, safety, and performance advantages of the gyroplane, and yet the helicopter's ability to hover, and that was with the Gyrodyne. The FAA defines a Gyrodyne as a rotor wing aircraft that powers its rotor for some portion of its flight, and that's normally hovering, takeoff, and landing. Forward thrust is provided by engine-driven propellers usually, or for advanced designs of ours would be thrust jet engines, high bypass turbines. And there were some interesting designs during that time, of course, the Ferry Rotordyne being the most notable. And because the tip jets are on for only 10, 15, 30 seconds during the takeoff part of the flight, the fact that they're not very fuel efficient becomes irrelevant. You're not burning them much during that flight time. The quest for speed. Practical design for a Vtol aircraft, a rotor wing aircraft that could fly at airplane speeds and not need a runway was elusive. Billions of dollars were spent through a variety of designs from almost everybody who made rotor wing aircraft. In fact, a number of companies that it was their only rotor wing aircraft were these attempts. The most successful of those designs were the Harrier, the Joint Strike Fighter, which is now just barely flying and hasn't quite resolved its vertical takeoff part, and the B-22 Osprey, the tilt rotor. And the tilt rotor is the only one that's rotor wing of that program as well. We believe that the attractive simplicity, cost, and performance benefits of sustained autorotative flight belong amongst that group that today are taking off and landing vertically. Some remarkable designs here. This helicopter, the Lockheed AH-56, there was a picture of that got me into the Army a long time ago. I made the mistake of saying, wow, I want to fly that in front of an Army recruiter. Next thing I knew, I was saying, your left, your right. Groen Brothers Aviation's effort. Gyroplane simplicity, helicopter hover, and high-speed flight. I belong to a CEO group that hires professionals to come in and teach us how to do things better. This was a speaking course. And the instructor said, I want each of you to get up and talk about what it is that got you here. How'd you pick the profession that you have? Where'd you get into? And my normal answer to that question when people said, how'd you start this, is that in the summer of 1966, I bought plans for a Benson gyrocopter kit in an advertisement in the back of Popular Mechanics magazine. And that is the image too, incidentally. And I could see myself in that thing over that water, flying along in that in such a way that even now looking at it gives me a thrill. I look at it now and I want to be there doing this very thing in that very aircraft. However, as I was sitting there preparing to talk before our group, it occurred to me that I've always wanted to fly. That's why I went to the gyrocopter. It wasn't the gyrocopter that started this thing. And I thought, where'd that come from? I was born on an airport. The end of World War II, the U.S. government had subsidized housing for disabled veterans. My father was a disabled veteran, and my parents lived in what was called Air Base Village at the Salt Lake Airport. It's where they lived when I was born. It's where they lived when I was gestating, or whatever the correct phrase for that is. and the housing was no more than 100 yards from the ramp. And so 1951, big round-motored engined airplanes running up, making racket day and night. Was that way through till I was about 6 months old, and my parents moved about a mile away from there to a house that was directly underneath the downwind leg of the airport. So for the first 18 years of my life, I was either right next to the airplanes as they were running up as a brand new baby, or they're flying over my house day and night. So I suspect that had a lot to do with how I got into aviation. I brought my plans to my high school shop teacher and asked to build it there. And he said, "Great idea. We love these kind of class projects, but you have to learn these other things first." So I did, year after year, and finally in my senior year, I demanded to be able to build it. And he said, "No. If I let you build that, you're going to die in that damn thing." I was furious. But this guy saved my life, I'm sure. Because you see, the Benson plans came with 2 books. One of them said, "Teach yourself to build the Benson gyrocopter." And the second one said, "Teach yourself to fly the Benson gyrocopter." Well, I finally taught myself to fly a Benson gyrocopter. This is me in my very first flight in my Benson B8M, same thing was over there. And, but I had about 5,000 hours of helicopter time by then. And if you can fly a helicopter, you can fly anything else. Everything else is much easier to fly, and this was an absolute cinch. But teaching yourself to fly is probably not a good idea. And, I'm glad I did. So I was years not understanding that one. Incidentally, 30 years later, our gyroplane ended up on the cover of Popular Science magazine. It was the summer of '66 when I bought those plans out of that magazine, and we were in there on the cover of 1996. After high school, I joined the U.S. Army to get into their Warrant Officer Flight Training Program. Vietnam War was raging. It was a perfect opportunity for a high school graduate to get into aviation. And only that, there was a real good chance I was going to go to war and be shot at, which sounded like fun. This is why they bring in us youngsters, because we're not smart enough to realize being shot at is not so much fun. In any case, in fact, this is the only picture I have of me in a helicopter in Vietnam. I know I'm hard to recognize up there, but I promise you that's me. And after the war, I flew helicopters commercially for a number of years, from all kinds of missions. And this particular one, I chose this image because I'm parked in a Bell 47 at the second highest peak in the Rocky Mountains in Colorado, nearly 14,000 feet in elevation. And this was my first jump takeoff. And the reason that happened is I get in the helicopter ready to go. It's a USGS, U.S. Topographical Survey. Mac makers were flying around. And we're finished to move off, and as I pull pitch to take off, the power needles, the turbocharger boost and the manifold pressure needles married. Every time I pull pitch, these are married, and the RPM would come off. So I don't have any turbo, I don't have any boost. So I climbed out of the helicopter and looked in there, and the engine, I could see that the exhaust manifold gaskets had blown out. And I had no turbocharger. And that meant that I didn't have enough power to get off of that mountain. And this is October in Colorado. And at 14,000 feet almost in October is a lousy time to be stuck on top of a mountain. We're more than 3,000 feet above the tree line. There's no walking out of there anytime soon, certainly not before dark and real cold. So, occurred to me, jump takeoff, gyroplanes. Spun up to the rotor to just below the structural red line, not the one painted on the dial, but the real one. Flat pitch, yanked in collective, jumped in the air, dove off of this cliff, and was able to go 20 miles. I mean, that's how high I was. I was able to go 20 miles before I was forced to land from not having enough power to stay airborne, and landed next to a gas station and called for help. So that's why this was there. Now, and from both my military training and my commercial experience, I learned that adjusting collective pitch in flight dramatically improved the autorotative performance of the helicopter. Now, this is not what the book says about it, but it's what I learned. And I learned this from, it began in flight school with an instructor who was an absolute master at autorotation. And from what he taught me and my own practice, I became a master at autorotation as well. Little did I know at the time I was going to spend my life in the field of developing those sciences. But it occurred to me that collective pitch is not normal to gyroplanes, and yet the helicopter's performance improved dramatically by adjusting it on the way down. I thought that ought to work. It led me to convincing my brother Jay to join forces with me to form a company to develop this science. He had the creative genius to come up with the how to do it. I knew what it needed to do, and between us, we got it right. Our first collaboration was on a novel about a helicopter pilot in Vietnam. The title of the book is Huey. It was based largely upon my experiences in Vietnam. But my two older brothers, Jay and another brother between us, Marty, were Vietnam veterans, and so we were able to tie in some of their stories into this novel as well. It was a New York Times bestseller, stayed in print 10 years, and about 8 printings. Very successful for a couple of brand new authors. Our first patents were based on collective pitch controlled rotor systems for gyroplanes, instantly variable between points. We got 3 patents on that technology. The first included 32 claims, which is the equivalent of 32 separate patents for that technology. These are both me flying these aircraft. This thing called the Hawk Point 5 got named the Hawk Point 5 by our staff once we started flying the Hawk 1. So the predecessor of the Hawk 1 had to be something. And Point 5 is what they chose. Again, I'm in both these pictures as what was then the company's chief test pilot 2. My shareholders convinced me that it was a bad idea to have the president of the company being the test pilot. They had a hard time convincing me of that, but they were right. A number of our advanced designs, the Point 5 again, the Hawk 1, the H2X, which was a side-by-side 2-place variant of the Hawk 1, our first of the Hawk 4 series piston engine helicopter. We went to a turboprop with that same aircraft, separate airframes, we have 2 of them. We then took a Cessna Skymaster, a high-wing Cessna Skymaster, took the rotor system off the top of the Hawk 4 and bolted it to where the wings mount on the Skymaster. And we had to turn the tail upside down, and we just pulled it off, flipped it over, and put it back, and the bolt holes lined up. Astonishing. And we had to change some of the wiring, of course, and move the lights, but otherwise it was that simple. And we flew that aircraft, and it was the shortest time from concept to first flight of an aircraft, and it flew like a dream. I mean, it was really great. And I'll tell you some more about why that's important. Yes. And then our Sparrowhawk gyroplane, which was a kit gyroplane, and the purpose of that was simply to improve the safety of the kit world. The kit gyroplane world had a terrible safety record, and that is because you can get anything to fly underneath an auto-rotating rotor, including really bad designs. And those designs were harming and hurting a lot of people, and so we got in there to try to cure that problem. All of this led to being chosen by the U.S. Department of Defense Advanced Research Projects Agency, DARPA, to develop a high-speed rotor-wing aircraft called the heliplane. Fast, long-range, helicopter-type hovering and vertical takeoff and landing with gyroplane simplicity was the goal. Performance goals: 400 miles per hour, 1,000 nautical miles of unrefueled range carrying a 1,000-pound payload. This was for a search and rescue class of aircraft. We met all of these conditions for our end of our phase one, which included a preliminary design review, about a 4-day-long meeting where we proved to the government we met the requirements, including a lot of tougher ones, like not tougher, 400 miles an hour on a rotor, nothing harder. Go to outer space, that's easier. I think. I haven't tried that one yet, but tough stuff. How we got to where we are is simply by having the best people. My brother Jay and I have, from the beginning, enjoyed the exceptional good fortune of being able to attract the best people. And this is in every field that we needed in order to make this what has now become an epic effort work, and including our investors. The list is long. I can't name them all. There are a few I must name. Robin H. Wilson, he's our Executive Vice President, Chief Operating Officer, a long time in top leadership of the airline industry, here tonight, and not only a key element to our success, but a close personal friend. Jaap van der Westhausen, Senior Vice President and Chief Technical Officer, has led our engineering department for more than the last 10 years. Al Wooddill, Senior Vice President, Business Development, again, more than 10 years with the company. Jason Chen, Vice President, Business Development for Asia, really an amazing Chinese family from, he's an American citizen, born here, but born in the U.S., but long time family relationships there have been important to our success. Walter Sonnenborn, he's our senior advisor in rotor wing technology, was 40 years as the senior scientist at Bell Helicopter, retired as their chief scientist, led all of their high-end programs. Lyle Campbell, Arthur Metz, Michael Sachs, Newman Petty, Steve Keeler, Ron Carlson, and many others. Each are investors in the company, but became very good friends. And our primary financiers, who wish to remain nameless, but really are the finest, most honorable group of people that I know. I apologize to those whose names I can't make tonight. We have also had the very good fortune of having, for our heliplane program, to attract an amazing team as well. In fact, added to our existing GBA team, it became the most powerful rotor wing science team ever assembled. To quote Mr. Ned Chase, who was chief of the U.S. Army's Platform Technology Division, Aviation Applied Technology Directorate in the U.S. Army's Aviation and Missile Command. He was one of the key observers for whether or not we passed our preliminary design review with DARPA. On that team also, Georgia Institute of Technology. They did primarily our analysis and a great deal of our design work. Adam Aircraft for airframe development, Williams International for engines and tip-jet motors. We also had senior engineering professors from the University of Maryland, Penn State University, Utah State University, University of Arizona, and Washington University in St. Louis. And a highly renowned team of aerospace engineering consultants, many of whom had earned the highest award given in the U.S. for achievement in rotor wing science, the Alexander Nikolsky Lectureship Honorarium. In fact, when Ned Chase, when he came up to say, "You have the most powerful rotor wing science team I've ever seen assembled," he also said, "You have 2 Nikolsky winners on your team." Well, I knew I had one, so I went and looked them up. We had 7, 6 of the last 10 on our team. That's the kind of power we were able to put together. And the government team under DARPA, they brought in the best of the best as well, which included teams from NASA and the Army's Advanced Flight Dynamics Directorate out of the NASA Ames Research Center in Moffett Field. In addition, they had people from industry they brought, including Dr. Ken Rosen, who is the retired chief engineer of Sikorsky, been there about 40 years and led all their high-end programs. An amazing talent. This most remarkable team led to more than 60 new patents for our company that are now either filed or in the process of it. The advantages of sustained autorotative flight enable aircraft to be both runway independent and economical, yet not be limited by the physics-imposed limitations normal to rotor-wing aircraft. Vertical takeoff and landing. High performance, which is higher speed, greater range, greater load carrying capability. Reliability. The design simplicity gives better reliability. Mission readiness for the same reason. There's so few things to go wrong, so few things to be worked on with the aircraft. Low cost. Again, the lack of complexity, cost of building them and operating them is less. And safety. A properly designed, sustained autorotative flight aircraft are the safest form of powered flight. And I say that without reservation. Our Advanced Hawk series gyroplanes, in the form of gyroplanes, gives runway-independent light aircraft. Our AeroHawk design, and these designs we used tools that we developed for the heliplane program. We couldn't use technology for the heliplane program because it's military, but we were able to use the tools that we developed to design the heliplane, to design these aircraft. AeroHawk is an advanced composite 7-place aircraft, primarily air taxi, tour guides, prop spraying, executive transport, airborne law enforcement. Our Shadowhawk, a tandem 2-seat high-performance aircraft in a type-certified aircraft, aerial patrol for commercial as an infrastructure patrol, power line, pipeline, waterways, roadways, land survey, those kinds of things. And for airborne law enforcement, police and border patrol, coastline patrol, security missions of all kinds. And then our Shadowhawk LSA, which is a light sport aircraft based on the same airframe as the T-seat Shadowhawk. And our intent is to use these existing technologies to develop a variety of much larger aircraft. Unlike transmission-driven rotor system aircraft, we're not constrained by growth in size. The scalability is based on pi, not weight of transmissions. There's some pretty cool designs. These are C-130s that we worked to convince Lockheed let us mount a rotor system to your C-130. They actually liked the idea, amazingly enough.
We announced the departure of Gyrodyne flights to Brussels and Paris.
That announcement will not in fact be made for some years, but this film shows the fairy Gyrodyne, the first vertical takeoff airliner, making its first flight between 3 European capitals. Takeoff was from London Airport, because at present there is no suitable heliport in the centre of London. A quick ascent to cruising altitude, and then the Gyrodyne translates into forward flight and heads for Brussels, cruising at 200 miles an hour, almost twice the speed of any other type of aircraft capable of operating between city centres. Apart from carrying passengers, the capacious fuselage is ideally suited for the carriage of freight, and bulky items such as cars and trucks present no difficulty. Being a versatile aircraft, there are obvious military applications for carrying troops, armored vehicles and equipment. Rear loading is made easy with the large clamshell doors. Recently, in the role of a flying crane, the Rotodyne accurately positioned a bridge over 100 feet long. A smooth vertical descent followed by a gentle touchdown in a space that need be little larger than the diameter of the rotor.
An amazing aircraft, the world's first runway-independent airliner. It was flying 200 miles per hour when most helicopters couldn't go 100 miles per hour. In fact, less than 100 miles an hour for most of them. Even today, the Rotodyne existed without the advantages of modern materials, modern aerodynamics. It would still be the fastest way from downtown London to downtown Paris. Even with this high-speed train, it would be an hour quicker if you could do it easily enough. We have an image that's very similar to this. This says ferry Rotodyne here. I have one, I've seen one anyway, but I couldn't find it or it would have made it to this show. And that says Westland Rotodyne. Westland inherited this program and in fact spent some time and energy trying to turn it into a viable program as well. The Groen Brothers Gyroline. Modernization of the ferry Rotodyne. Electronics, all modern. Glass cockpit. Amazing what's available now for cockpits. Rotor system, totally different than what existed in those days. Some interesting things that have had to change. Rotor blades, silencers and modern materials for these tip jets. Ferry had worked hard on bringing the noise from the tip jets down and had successes. I mean, they had made some significant improvements in that, and we've been able to take that a bit further ourselves. Advanced vibration control, that has to be comfort. Vibration's hard on people and the equipment itself. Advanced propeller technologies, advanced propeller gearbox technologies making them lighter. Composite structures, engine technologies, I mean, the things that now can be done to prove what that marvelous aircraft could do 50 years ago. It's astonishing that it hasn't yet been done, that these aircraft aren't flying all of us around these days. Our baseline design criteria sizes from 19 to 100 passengers, so that could even go bigger if there were markets for such things. We think commuters, 100 passengers probably as big as that's likely to go. Cargo variants of the same aircraft. 350-mile range with IFR reserves. At 240 miles per hour in cruise, that's an hour-and-a-half flight. Certainly not uncomfortable. Operations for certainly vertical takeoff and landing or ultra-short takeoff and landing. Give us a yellow box on the ramp of any major airport that's 100 meters square, and we've got a Gyroplane vertiport, an Vtol airliner vertiport. Pressurized, all-weather, including flight into known icing conditions, which is rare for rotor-wing aircraft. And the reason we can do that is because we're pumping hot air for the tip jets, compressed air out to through that rotor system to the tips to add fuel and spark to, and it's hot air. I mean, they call it cold flow, but 300 degrees doesn't seem cold to me. So we get plenty of heat when we need it or want it in that rotor system, even if we're not burning the tip jets. Applying 21st century technology to the Cierva and Rotodyne experience. Safety, reflecting Cierva's first victim, stall-free, and stable flight. After takeoff, it operates as a gyroplane in all flying conditions. During engine failure emergencies, the aircraft has a long glide, about 3 times that of a helicopter engine off, and will land softly anywhere the rotor system can fit. Height velocity curve, also called the dead man's curve, that area that if your engine fails in a rotor wing aircraft, you're going to hit hard, almost doesn't exist for this aircraft, and is only during the takeoff phase. And because of the weight of those rotor blades, the tip jets of those rotor blades, it may not exist at all. We'll find that out during test flying. Simplicity, reflecting Cierva's second dictum. Gives us low operating costs, simple mechanisms, fewer things to fail, which again, fewer safety critical parts, which permits higher utilization. Our ideas in developing this aircraft is to take an existing high-wing commuter airliner and modify it. We did so with the Cessna Skymaster. This is why we tried that, is to put a rotor system on a high-winged airplane and will this thing fly? And so our idea is to do the same thing with a commuter airliner. It's relatively easy design modifications. We mount the rotor to the same wing box that the wings are mounted to, leaving the wings. Significant savings in the gyroliner development time and costs. The design of all of the aircraft systems and the manufacturing processes. And these savings exist because for the airframe part of this vehicle, the engineering that was performed in order to get the type certification for the airplane is usable in a new type certification for a gyroliner aircraft. We don't even have to change the number on all the drawings. We're just saying the package in the cover letter says these, the numbers from this series are for the airframe part of it. The things we will have to do are the changes that adding a rotor system caused to that airframe, but we're talking about probably 80% of the engineering necessary to type certify a commuter airliner. Is work finished, can be handed over. The parts suppliers, the job of finding and qualifying all of the companies that are going to provide you with all of the pieces that go into these aircraft is an enormous task, an expensive task. For the airframe part of it, all of that has been finished. The tooling, designing and building the tooling and getting all of that right, which means redesign and rebuild and so on. For the airframe, everything but the rotor system's already done, paid for. Training, the cost of the people that just simply learning how to put all that together, the learning curve, it's all already done. So adding a rotor system to these things certainly adds some complexity and changes the structure and so on. They'll have to be added to the certification effort, but huge savings in time and dollars, and we're convinced it will work. Now we're going to lose some performance because we're adding a lot of weight to an existing airplane, but these airplanes are all, nearly all 1,000-mile plus aircraft. We're talking about 300 miles. Make up for the difference in weight we're adding by carrying less fuel for those, for when you have a full load of people for the project. Not optimized, ground-up designs would be better, but to start with, this would be a great way to make that work. Runway-independent airliners will transform the airline industry by providing rescue from airport gridlock. 40% plus of the flights that go into the major airports around the world, in America it's nearly 50%, are commuter distances, 350 miles or less. All of those flights, or nearly all of those flights, can be off-runway operations now with a gyroliner, which permits these airports to all use their runways for the things that can only use runways, and that's the big airliners, dramatically improving the throughput at these airports. But it also creates a downtown-to-downtown operation. For the terminal footprint about the size of a football stadium, no runways, just the terminal and the ramps necessary to operate these aircraft. We could have downtown-to-downtown operations every major city in the world for gyroliners. and a terrific opportunity for real estate development too, because remember when cities want to bring these football teams to town, it's because of the human throughput to come into those. And with an air terminal, you've got throughput day and night. Expansion of the Heathrow Airport. Adding a third runway became a collision between the economy and the environment, and looks like it's not going to happen. Without direct action, Heathrow's hub status is going to diminish. Airlines will continue to substitute larger aircraft on longer routes for smaller aircraft on shorter routes. Can't fit in the little airplanes. Opportunities for connections at London Heathrow will diminish, and thus transfer traffic will decline, causing a disadvantage to UK-based airlines. The diminished options for business travelers between London and those short to medium distances will see London's importance as a business center decline, in our opinion, if that issue isn't resolved. There are alternative approaches. Build a new airport, such as the Thames Estuary Airport, which is probably going to be too expensive and environmentally unkind, meaning that just getting through those two hurdles will probably keep that from happening. The other opportunity is to add capacity without really adding runways, which is build high-speed trains, improve the ground transport network, or runway-independent airliners. Rail service is not likely to be the solution. Heathrow Airport Limited's analysis suggests that with remote interchanges, flight substitution would be minimal, about 5% improvement to that airfield. With interchanges, integrated interchanges, substitution would be twice at 10%, but at a significantly higher cost. Runway-independent gyroliners, on the other hand, provide vertical takeoff and landing, trip times comparable to commuter jets, as a matter of fact, in that distance segment, because no taxi time, no waiting in line for runways for takeoff, no fooling around with airline ATC, air traffic control stack. Rolling aircraft can come in underneath all of that. Because of the absence of scale limiting transmissions that go as big as the market needs for that kind of aircraft, as well as the advantages available from control simplicity. Operates like an airplane, has the same kinds of costs that an airplane would have. And safety, free of stall, has the same kind of safety characteristics of the gyroplane. If the Rotodyne had only survived and been allowed to evolve, Heathrow and many other world airports wouldn't be in the trouble they're in today. And I might add, I probably wouldn't be up here talking about it today either. I'd probably be having to do something else. Evolution, however, finds its way. There's a cover of Flight magazine, January 1953. London to Paris and back. An idea even more relevant today, in our opinion.
Groen Brothers Aviation is the leading authority on the science of gyroplanes. Gyroplanes combine the vertical takeoff capability of a helicopter with the speed, safety, and efficiency of an airplane. The Aerohawk gyroplane is essentially an airplane that doesn't need a runway. The Aerohawk is Groen's most advanced production gyroplane design. The Aerohawk gyroplane is a 7-place vertical takeoff and landing rotorcraft that will cruise at 300 kilometers per hour with a range of up to 900 kilometers. The Groen Brothers Aviation Aerohawk gyroplane is designed as a powerful and versatile aircraft for a wide range of applications. In a competitive business such as commercial air tours, a gyroplane operates at a much lower cost per seat mile, so the savings to tour operators are substantial. Also, a gyroplane can fly more tours per day. Together, lower cost and higher utilization result in increased profits. And the same is true for corporate transportation. Additionally, increased productivity comes from direct point-to-point travel and the elimination of typical airport delays. Demand worldwide for airborne law enforcement, security, and border patrol is rising faster than budgets. The favorable economics of a gyroplane permits safe eyes in the sky where it would otherwise be unaffordable. Groen Brothers Aviation has designed the Shadowhawk as a high-performance tandem two-place airborne observation platform for law enforcement and power line patrol. Vertical takeoff and landing is possible when a gyroplane has a GBA patented collective pitch controlled rotor system. A gyroplane, such as the turbine-powered Hawk 4, is an aircraft that always flies in autorotation without engine power to the rotor. This is called sustained autorotative flight. A helicopter's rotor is constantly powered, providing both lift and thrust, making it extremely complex and expensive to build, operate, and maintain. In a gyroplane, the rotor provides only lift. Thrust comes from an engine-driven propeller. As the gyroplane is thrust forward, the airflow through its unpowered rotor causes it to spin, much like wind through a windmill, creating lift. A gyroplane always flies in autorotation, so it does not need the complex and expensive drive system and tail rotor of a helicopter. This results in major cost savings. Because a gyroplane flies in constant autorotation, in the case of a power failure, it can be safely landed. And unlike a fixed-wing airplane, a gyroplane cannot stall. Even the recreational GBA Sparrowhawk can safely perform a no-power landing. An experienced pilot can do this easily with any GBA-designed gyroplane. With the performance, cost, and safety advantages of sustained autorotative flight, Groen Brothers Aviation can see beyond the widespread adoption of the AeroHawk gyroplane to the development of gyroplanes capable of a wide diversity of applications. The time is perfect for a spectacular period of growth for Groen Brothers Aviation as a result of their unparalleled experience and engineering mastery in gyroplane technology. As a result of its leadership in the field of autorotation, Groen Brothers Aviation was chosen by the U.S. Department of Defense to be the prime contractor on the successful first phase of the DARPA heliplane program to design a vertical takeoff and landing rotorcraft capable of 400 miles per hour, twice the speed and with twice the range of a typical helicopter. The Groen Brothers Aviation vision for the future of passenger transportation worldwide is this: runway-independent commuter airliners. Operating from major airport terminals, they will provide fast, affordable, point-to-point transportation while helping to alleviate runway overcrowding with their vertical takeoff and landing capability. Groen Brothers Aviation's future Gyroliner is an airliner that doesn't need a runway and could therefore help to solve the world's growing transportation infrastructure shortfall. And the future begins with the GBA AeroHawk gyroplane. With a combination of safety, reliability, performance, and economy, the GBA AeroHawk gyroplane is unbeatable. We are now at the point in history where global budget constraints, airport overcrowding, and security needs make the emergence of these safe, reliable, and economical runway-independent aircraft absolutely necessary.
The solution to runway overcrowding? We think the gyroplane, an airplane that doesn't need a runway. Mankind went from the Stone Age to the Agrarian Age to to the industrial age, and then finally to the information age. And we think now the transportation age as the latest bottleneck to progress can be solved through runway-independent aircraft. Runway-independent airliner, we think, will have it as an important an impact on transportation as the advent of the jet age. Thank you so much for permitting me to come and speak to you all. I'm, again, highly honored. Thank you for your attention.
Thank you very much, David. That was fascinating. I had a bit of paper on my desk here, but I think the president must have nicked it. Had a few notes on it, but it's okay. I've read it once or twice, I can remember. David, would you care to take questions?
Oh, sorry. Yes. Questions?
Fantastic. Any questions?
I know I've held you longer than normal, but forgive me. Sir?
David, what happened to the DARPA projects?
The two wars and an economy on its back. I mean, we finished the phase 1 at the end of 2007, would have been into the phase 2 program by spring of 2008. You may all recall what happened about then to the economy. You know, we were so heavily invested in heliplane, meaning that we didn't have the resources to do anything else as far as human resources. It was eating up all of our capability. So we did very little else. And so for phase 2 then didn't happen simply because there just wasn't money available to it. Economy was in bad shape, 2 wars going on. It continues to exist as a Department of Defense program, but it just hasn't been able to get secondary funding yet. We expect it will. We certainly hope it will. We know that the breakthroughs we've made are going to change how everybody gets around. I mean, these are huge, important breakthroughs in rotorwing science. Still has to be built and tested, but the numbers shake out and held up to a very stringent peer review. Sir?
Your program, your model for a transportation system. Oh, thank you very much. Switched on. Yes, it is. It's very reminiscent of the studies conducted in the 1980s for a tilt rotor transportation infrastructure across the US with the FAA, with very heavy, etc., etc. Aerospatiale down in Marignane were running similar programs. All that survived out of that really is the V-22 Osprey for the US Marine Corps. Why would your program be successful when that one sort of fell by the wayside?
One of my favorite questions. Thank you.
Glad to oblige.
There have been a number of airlines in the world over my career that used helicopters as an aircraft. And helicopters can't work, and they can't work primarily because of the economics. There are other reasons. They're noisy and they're uncomfortable to ride in, and they've got safety problems, but it's primarily economics. You can't sell seat prices to ride on these things at a rate high enough to make them profitable to do, and that's why they have failed. The tilt rotor is far more complex, far more expensive than even helicopters are. And so until helicopters can work in that market, which thus far has not happened, the tilt rotor is not going to work in that market. So essentially economics, that's it. And with a gyro liner, we're talking about an aircraft that has a cost per flight hour that's a bit more than an airplane, probably 10, 12, 15% more in cost per flight hour, but because we're not spending all that time on taxiways and ramps, the cost per seat mile is going to be very comparable to what a light aircraft is, a light airliner is. And the advantages of not having to be tied to that runway. I mean, the cost of buying a gate that uses a runway is huge. By not having to use that runway, those differences in operating costs will be easily made up, in our opinion. It's going to head this way. The world needs it. And you can't find a place in this world that doesn't have this problem. Either they've got lots of runways and the runways are all way overcrowded and they need to build new ones, or countries like China that have no runways. It doesn't matter where you are, building new runways and new airports is huge and expensive and hard to do.
What kind of altitude are you operating?
I'm sorry?
What kind of altitude do you anticipate operating at?
Normally, gyroplanes are like helicopters. You're going to operate at altitudes you can breathe normally at. An airline serviced aircraft would have to be pressurized for not only passenger comfort, but be able to get high enough to get the speeds that we're talking about. So they would be able to operate 25, 30,000 feet. Our heliplane was designed to fly at its speed between 30 and 35,000 feet.
Tim Robinson, Aerospace International magazine. Thanks very much for the vision of the future that shows us all escaping the kind of the trap of Heathrow. Two quick questions. Firstly, have you looked at the noise problems of the noise footprint in any city environment? Do modern CFD designs, modelling mean that can be solved? And secondly, can you say something about sort of competing designs like, car-to-copter, about how other people are going about the same sort of, solving the same sort of problem?
Okay, thank you. The question related to noise in our heliplane program, which is a tip jet aircraft, we had to be able to design a rotor system that had rotor noise while tip jets burning no more than what a comparably weighted helicopter would be doing. And in this case, it was a UH-60. So the aircraft's not going to, with tip jets burning, not noisier than a UH-60 for the heliplane program. The government, but during that effort, we came up with some ways to make it even quieter that DARPA spent some money on to develop too. So we think we've got some pretty good ways to keep those tip jets from being a problem, just from the noise being generated. However, again, you're only burning them for a very short period of time during takeoff, and the only time they're real noisy is just for a few seconds as you're blasting off out of the ground. Because noise is a function of VJ, velocity of the jet exhaust out of that tip jet, and it's a factor of 8 to the sound being created. So we don't have to come off much in power demand in order for those tip jets to quit being a problem noise-wise. And anybody that flies helicopters knows the big power demand is at hover, and as soon as you pass into translational lift, power requirement goes way down. And at that moment, those tip jets are no longer causing a noise signature that's going to bother anybody. Noise is not going to be a problem. The other thing is this airplane can climb at a rate nearly double what a comparable airplane would be in that same class. So all of the noise it's generating is going to happen over the airfield by the time it clears the fence. In fact, in our heliplane program, coming up with a plan that said, well, this is how we meet the noise requirements. Well, the helicopter noise requirement is a flyby. Well, the jets are off, so they said, well, you can't do that. It's got to be do it more like an airplane. Well, the airplane one is the microphone's at the end of the runway. Well, we're 5 miles in the sky by the time we're at the end of the runway, so that wasn't going to work either. Essentially, the issue is noise is not going to be a problem. It makes noise. It's noisy during that few moments. It's localized and it doesn't last long. Secondly, Jay Carter, a smart guy, neat guy. I like him and known him a long time. Been trying hard to make a success of sustained autorotative flight as well. If we're right about what the value of this technology, it's going to support lots of innovators like myself and my company and Jay Carter's company as well. We hope he's real successful. We think he can be. His approach is different than ours, essentially.
Just one here.
David, as a good piece of exam, you concentrate on the civil application. You must see a military application to some of this.
We do.
And the one thing that I could see as a possibility is that brownout isn't quite the same problem with a landing gyroplane.
Yeah, in fact, the heliplane program, rotor downwash was an important element to it. What David Gibbings asked was in fact, how he phrased was being a peace-loving man. We're talking mostly civil, but there are plenty of military applications for this type of aircraft, even without the heliplane. I mean, imagine troop carriers the size of the Rotordyne. I mean, the Rotordyne is a bigger aircraft carrying more people or more cargo than America's largest helicopter. It's bigger, more capable, near 50% faster than today's most modern big helicopter. So yeah, the military is going to absolutely want these kinds of technologies. And rotor downwash is a big problem. I have friends in the Marine Corps that are involved with the V-22 program. And Walter Sonnenborn, who's one of our chief advisors, was a lead engineer, led the engineering team for the part of the engineering team for that Tiller program. These guys said that the downwash off of that was peel the clothes off a Marine. Well, that might be an exaggeration, but it gives a point. It'll pick up rocks as big as my fist and throw them at you. That's how much downwash is coming out of that rotor. And so brownouts, the things where you're coming in and hovering and pushing a whole bunch of air down, are a lot smaller problem for gyroplanes. And certainly if you're not hovering, if you're able to land and take off without hovering, that problem nearly goes away. Sure.
Can you please outline? Oh, thanks a lot, but I can shout quite loud. Can you please outline how do you achieve the vertical taking off in your small 7-seater and the 2-seater gyroplanes?
Yes.
Is it through tip jets or pre-rotating or some system I'm not aware of?
We use power takeoff for vertical takeoff in those smaller aircraft, or any of them really, including something as big as a commuter airliner. We don't need tip jets. Pre-rotate the rotor system to about 140% of operating RPM, which incidentally is a tip speed similar to what a helicopter is at hover. So we're not talking about real high RPM. In-flight RPM is about 2/3 of what a helicopter in-flight RPM is. So pre-rotate to 140% of gyroplane in-flight RPM, flat pitch, lift up on the collective pitch control, which disconnects the pre-rotator, this power takeoff from the engine, using the inertia, the momentum energy of the rotor blades to provide that vertical component. Now you're also full throttle on the engine, so it lifts off and accelerates forward. You may remember an image or two from that video showing it lifting into the sky. It's simple, it's easy to do, the aircraft's stable. As soon as you've accelerated forward, the aircraft's already in auto rotation and stable enough, you can let go of the controls.
How high can it get only when you pre-rotate the rotor and you wait till the inertia stops pushing you up? If you see what I mean.
The answer is how high we want it to go. It's a matter of what kind of tip weights you put in there and how fast you spin them. So if you've got an application that requires you to leap 100 feet straight in the air, you can. I can't think of an application where we would want this aircraft operating that would require that, because there are costs associated with it. You put great big weights in the tips of those rotor blades. You got a gyroscope out there that's heavy that doesn't want to change the plane it's flying in. So your lock numbers go way down. I mean, these are a balancing act. How much do you want? Well, we're talking about clearing a 50-foot obstacle about the same distance that the helicopter, a little better actually than what a helicopter of similar weight, similar capability, taking off. We can clear that 50-foot obstacle in at least as short a distance. And more jump than that is cost that we don't think the aircraft ought to have, but it's doable. I mean, sure.
Thanks a lot.
Looking for, oh sorry, you're helping out, not asking questions for you. Eric here incidentally came over and worked for our company as an intern engineer some years ago. I'm very delighted to see him. I'm surprised to see you here, Eric. Thanks for coming. Sir.
Given that ferries have developed the concept for you and you're going to use an existing airframe perhaps, how soon can we expect to see this thing fly? The second question, what are the big problems you face? What's the biggest problem?
Answer your first question is, let me put it this way. There's one thing that I've been consistently wrong at, and that's predicting when. And I don't even want to try again, but as I've said many, many times, soon, I think. So secondly, the problems that we're faced with are no longer technical, and haven't been technical for quite a while. I mean, we really have a solid understanding of the technical aspects of this science and what it's going to take to get from where we are to meet all of the goals that we've talked about here. What has been our bane is being properly funded, or lack of being properly funded. When my brother and I began this program, we had a much smaller idea about what gyroplanes ought to be doing because we didn't know anything about what they had been doing. And so, like the typical American way, you spend all your own money first. Then you spend your family's money. Then your friends' money. Then your friends' family's money. And pretty soon, you have to start spending strangers' money. And this is why going public, which we did. But it's been a continuous struggle for us to stay funded well enough. To find the final answer, and that is we now, our next move forward, we fully expect to do so from a fully funded effort. We're not going to be dragging it out like we have all these years from Hackathon. So, you had another question?
Yes, could I ask another one? I'm remembering that years ago, Westlands had a helicopter operation, I think in Los Angeles, with a W-30 helicopter. And that aircraft ended up taxiing for miles because that's the way the airport wanted them to operate. Have you spoken to the airport operators, and are they going to let you do what you want to do?
We think so. We have spoken to them, of course, and I spent my life, in the first half of my adult life, flying helicopters in that very environment, so I understand the problems. They make those helicopters taxi so far away because they're being driven by a rotor. We'll taxi with that rotor stopped. We would taxi out to the 100-yard square, spin up the rotor and fly off from there. So we're creating no downwash, which is what airplanes hate with the rotor in this aircraft until we're at the takeoff point. So I don't reckon that there'll be those kinds of problems. And remember, they're going to be highly motivated about the problem of solving this runway overcrowding. Certain things they'll tolerate better than they ever have before, right? Is our estimation. Sir?
Thanks. Take one more, shall we?
So just further to that, do you foresee the development of additional heliport infrastructure?
I do indeed. In fact, I think the real big money to be made from this technology is going to be just that, infrastructure. The trickle down in jobs creation is going to be most affected by what happens in these major cities where, in America, if you're a baseball team or a football team or a basketball team and you want to uproot and move to another city, you get cities willing to fist fight with each other in order to get you to come there for a reason, and that reason is economic development. They're going to put you in some blighted area of the city, knock down, through compulsory purchase, take over some big chunk of the worst part of the city, knock it all down, build for you a stadium, and then develop the land around that stadium for high human throughput types of businesses. The advantage that the Gyroliner brings is everybody can have one. It's not just the finalists and lastly one city that gets to buy, that gets you as a football team there. Everybody gets one. They're going to be in every city, and in many cities more than one. I mean, Los Angeles Valley has 49 airports right now. 49 airports in Los Angeles Valley servicing that metro city. So there'll be multiples of these, and you take people and push them through an area, a certain amount of dollars, and fall out of their pockets. Economists know what those numbers are, and so it's an easy calculation to figure out how that land will value. Including all the employees are going to be made by construction of these downtown airport terminals. And the rest of it. I mean, just think what happens to things like electric cars. You're flying from a city center to city center. Electric cars are going to make a lot of sense now because I'm just going to go a few blocks downtown from where I've flown into to my meetings. Some of your little parks and plugs in, that kind of stuff. I mean, it'll have a huge impact on our transportation system.
Well, go on then. If you're okay, David, one more?
I'm okay.
Okay.
Sir.
I would have thought there'd be a big uptake from police departments and paramedics, emergency services.
I didn't catch the first part of your question, but the value that this type of flying brings to emergency services and law enforcement is going to be from a visual recon point of view. Right now, many law enforcement agencies have helicopters, and they're using them for visual recon. And the reason they are is because they can fly low and slow relatively safely. You can't do that in an airplane. But taking that asset and putting it on the ground is not a good idea for the airborne law enforcement guys. And so if you have a search and rescue, somebody's missing, you're trying to find them or use them for those, you wait till you find what you're looking for and then bring in the air medical helicopters. And the helicopter is more suited to air medical than a gyroplane is going to be. Because the helicopter can hover. It can get itself into impossible to land to other places otherwise. So we don't see this as a replacement to helicopters, simply as an economical way to increase what helicopters already give us at significant cost. Was that along the lines of what you're asking?
David, thank you for your indulgence. I'm going to draw a line there, but I'm sure we'll be next door shortly, and I'm sure David will be happy to take questions in there. If I volunteered, if it's something that he regrets afterwards, I apologise. I wonder if I could ask Phil Steer if he could just pose a vote of thanks, please. Phil is the chair of the Specialist Groups Committee.
Well, thank you very much indeed. As always, you write some notes down. The words that come to mind here is vision, focused determination, and passion. We have seen passion. And we've also seen a good approach. I mean, there's evolution comes to mind. But the interesting thing is you're willing to take on the challenge. And there are many challenges. And they're not just technical challenges, as you alluded to. Then it gives results. Well, your contribution to aerospace is significant, particularly in the gyroplane area. And also, it's interesting to you're sensitised to really community and how aerospace can apply, which is important in current day and age. So it brings me to the last topic, which is relevance. And I look at sort of that there, and first of all, it's very relevant that you be presenting at this particular end lecture relevant to Cierva. But more importantly, I look at that and look at that and say there's a future. And there's the future, not just the past. So I thank you very much as well.
David, I'm going to bring things to a close now, just to say thank you again. I think you brought us properly full circle back to where Dr. Bennett started all this off. And can I ask the President to come back to the stage and just make a small presentation? I'm just slightly concerned that my notes say here. And there. That's right.
Just before I make this presentation, I would like to just say one thing, because Ken Wallace is here. Many years ago, when I was a student, I lodged in the home of a guy who was a Batman at the Priory. And he said, do you know, one of my officers is building an aeroplane in his room. I'm really privileged to meet that strange guy who was building an aeroplane in his room. I also feel very privileged to have attended this lecture, and we've got a small token of our appreciation. It's in spite of it being a big pot, it is a small token of our appreciation, which is in here. It's a difficult to open box, so I hope it's not delicate inside here. next time we'll open this first. It'll open like just the box, but inside the box, impossible to open.
Was it first?
Is a small token of our appreciation.
Gorgeous. Thank you so much. Very kind of you.
And I have another.
I can see myself and my future.
The only problem is it doesn't fly, but you might try.
That's what you think.
There is also another aspect to tonight. Fellowship of the Royal Aeronautical Society is for those who made significant contribution. We've heard tonight in the challenges that you have overcome to get a gyroplane flying as you have. And one of the privileges of the post of the President is that we are able to identify those who haven't got around to fellowship yet and offer presidential invitation to fellowship. So it's a great privilege for me to award you the fellowship.
Wow!
Thank you. In that case, perhaps I could just say a word of thank you again, and also thank you to Augusta Westland, who are very kindly sponsoring the reception outside, and invite you all to join us for a few drinks, and we'll also find out officers.
Thank you. Thank you. And thanks to all of you this morning.